Okay, thanks. All right, so welcome back to the second part of my talk. What I'll talk about next is um, new error models, so insertion, deletions, and erasures, and in particular, locally decodable codes for insertion and deletion, and locally recoverable or local reconstruction codes for erasure coding. So I'll just kind of start a little bit slowly with insertion and deletions because we haven't had any kind of intro onto this model this week. And let me quickly define the edit distance between two strings x and y. It's the minimum number of insertions and deletions to transform x into y. Okay, so for instance, in this example here, the edit distance between x and y is 4 because I have to delete 0 and insert 1 in the first position and delete 0 and insert the 1 in the third position. Okay. One can, if you think a little bit about, one can show that the edit distance between two strings is lower bounded by twice the Hamming distance. So if the edit distance is large, then the Hamming distance is large, but the edit distance could be much smaller than the Hamming distance. So one can define codes for insertion and deletions and decoders that are able to recover messages. This is in the standard classical decoding setting where we're given a received vector of size n, and we want to decode to the message x when we have, let's say, constant fraction of insertions or deletions. And just as before, one can define the relative minimum distance of a code to be, so here the normalization factor is 2m because we want it to be in 0, 1. We also have the same notion of rate, the same goals as before. We want good code, so codes with constant rate, constant distance, so this would be in the classical setting, and algorithms that are efficient for both encoding and decoding. Okay, so insertion deletion codes were introduced in the 60s by Levenstein, but only in 1999, Schulman and Zuckerman came up with the first construction of good codes that also have efficient encoding and decoding algorithms. So about 30 years later. However, recently people have really picked up on insertion deletion codes, and there is quite a lot of work in the recent years that kind of try to get the best parameters and efficient decoding and less decoding variants. And if you want to read more about it, there are some excellent surveys that I'm listing here. Okay, so what about local insertion deletion codes? I found this quote in a paper in Nature Materials where essentially, so people who work in DNA storage and DNA storage technologies, they care about random access into their data so that they can quickly retrieve files from a database. And this is exactly, right, so ability to efficiently retrieve specific files or arbitrary subset of files, this is exactly the motivation that we have for constructions of locally decodable code. So in particular in DNA storage, the type of errors we see are insertions and deletions. So that's why DNA storage is kind of an application domain for such codes. Okay, so how do we start even thinking about what kind of, how can we come up with locally decodable insertion deletion codes? And maybe the first thing to think about is, well, we have all these constructions, all this literature on Hamming locally decodable codes. Can we somehow leverage it to get insertion deletion codes? And it turns out that that's indeed the case. So The first paper that considered locally decodable codes is by Ostrovsky, Parskin, and Chernyavsky. And they can prove the following statement, that if you take a Hamming locally decodable code with Q queries, correcting a delta fraction of Hamming errors, you can somehow massage it into an INSDEL, insertion deletion, locally decodable codes, where the query just blows up by polylog M. So I'm kind of switching from K to N in the first part of the talk to N to M here, but hopefully it will be clear from the context. So polylog length of the code word, blow up in the query complexity, and with a constant blow up in the rate and constant blow up in the distance. Yes?
Sorry, is there a sigma different from bits or?
Yeah, this is a binary code. So they build a binary code.
What's the requirement on sigma? Can sigma be any alphabet in the start code, or?
There is a sigma somewhere in here, somewhere in the thetas, but yeah, I don't remember exactly.
Okay. So instead of instill, can you just consider a deletion only model?
Just a deletion. Yes, that would suffice.
Normal result, like instead of insertion.
Oh wait, no, I think you need insertion and deletion.
I see.
Yeah, that's a good question.
It's not. Okay.
That's a good question. Yeah. Although, let me think about it. It might not be. I'm kind of blanking now on that, but deletions might be just enough. Although let me think about it. So, anyways, we can take Hamming LDCs and pack them up into insertion deletion LDCs with not too bad of a loss in the parameters. And the only bad thing that happens is that the query complexity blows up a little bit. So this is something that we also reproved a bunch of years after this result. We kind of rediscovered and reproved it, and kind of that's what got us interested in this area. And by now there are many other works on locally decodable codes. So let's quickly just kind of see what this reduction gives us in terms of INSDEL LDC trade-offs. So if we take they had a marked code, they have Hamming LDC with query 2 and exponential length, we essentially get nothing interesting. So that's we can skip it. For constant query complexity, the upper bound is sub-exponential here, but because of the blow up, we get pretty bad rate in the transformation as well. And the only regime where things start to be interesting is this polylog M regime, where you get polylog and query INSDEL LDCs with message length that is sub-quadratic. Okay. Okay. So and the next interesting regime is the kind of n to the little of 1 query complexity, where you get constant rate. So with log n to the log n queries, you can get a constant rate locally decodable insertion deletion codes. Okay, so I'm just going to next give you a little bit more intuition about this reduction, just to see how we work with insertion deletion codes. This is going to be a very high level overview. The reduction is perhaps something you would expect. It's a concatenation. So we have an outer code, which is a Hamming LDC. So this code is going to be able to decode each bit if Hamming errors occur. And then we're going to compose it with an inner code, which is the Schulman-Zuckerman code that I just mentioned before, which essentially has constant rate, constant distance, linear time decoding. So we're going to obtain a binary code that looks like this. So we take the LDC code word, and we're going to break it into chunks. And then we're going to kind of label each chunk by its position in the code. And we're going to encode with the Schulman-Zuckerman code both the information in the chunk itself, as well as the position of the chunk. And that's kind of like the hard thing in insertion deletion, is to figure out where each bit ended up, right? Because with erasures, we know exactly where the data is. With and so is the case with bit flips. But I mean, locations stay the same. That's what I'm trying to say. But here with insertions and deletions, locations might change, and a lot of work might be needed to figure out where each location ended up. Okay. After this step, we add some extra buffers to kind of make sure that we can separate the information bits from kind of each other. We separate the information bits. And each of these buffers, as well as the code, is going to have size about log m bits. Okay, and just to remind you, this is essentially where the blow-up occurs, the log m blow-up. Okay, so if there are no errors, how do you figure out the value of a message at position I? We simply simulate the local decoder, the outer decoder, right? It's going to tell us where the queries, what queries to make. Then I go to the position of the queries, I decode, figure out what the value was at that query, use the outer decoder, and output the bit that I care about. Okay, so things are great if there are no errors. We just need to decode these information chunks, and we have good decoders algorithms for that. And as I mentioned, the challenges here are searching for an index in a corrupted code word, and also finding the buffers turns out to be a challenge. So the properties that are helpful of the Schulman-Zuckerman code are essentially rate distance and decoding time. But also there is this fourth property, which essentially says that for every interval of length k, there are many ones in the encoding, so the weight is large. So we have fractional Hamming weight at least 2/5. And the implications of kind of like where does this help us? So 1, 2, and 3 implies polylog m query time. Right, so we need to decode each information bit in log time. And the property 4, it helps us figure out where the buffers are, because we can simply kind of test the density of ones in these blocks and figure out where we have information blocks and where we have buffers with just a few queries. Okay, so how do we find block J in the corrupted code word with insertion deletion errors? The idea here is essentially a binary search, but it's in a noisy setup. So the reason it works is because most of the blocks appear in the correct order, and also there are some nice combinatorial property of the bits that we can actually recover, the positions that we can recover. So I don't want to say too much about, but this is a kind of like a cute toy problem to figure out how do you perform noisy binary search on an array that is kind of that are far from sorted. Okay. So this leads us to a question of the form, is binary search inherent to locally decodable? Yes.
Right now we're assuming an alphabet of binary, right? But in DNA, the example, right, it was,
Yeah.
I'm presuming it's base 4. So then do you
Right.
think that would also substantively change?
Yeah, that shouldn't change anything.
That shouldn't, even though each character would have more.
There are ways to, I mean, it's constantly many bits. Asymptotically, it should be exactly the same.
Okay.
Yeah. Okay. So is binary search inherent to locally decodable codes? And if you see what I'm driving at is, can we get locally decodable codes with fewer queries? Like, do I have to perform log n queries, or maybe I can do something smarter and get constantly many queries, insertion deletion. So this is in some sense an open problem. I'll tell you more about it soon. But in kind of recent-ish results, where we're interested in precisely this question: what happens in the constant query regime? Right? We have an immediate two-query Hamming LDC. Right, the Hadamard code. Can we come up with constantly many queries, insertion deletion code? So we tried very hard and we couldn't come up with anything. And it turns out that such things don't exist. If we're looking for linear insertion deletion codes, they don't exist with two queries. That's one of our results. And in general, we kind of reproved the inherited lower bound from the Hamming case of exponential in code word length. So these extend to exponential lower bounds for constantly many queries, and even to the regime of about log n over log n. So anyways, these are kind of like the first results about locally decodable insertion deletion locally decodable codes with constantly many queries. Some of these results can be extended in the case of relaxed locally decodable codes, right? I just mentioned that for relaxed locally decodable codes, you actually can get a dramatic drop in the code word length for constant query, because you're allowed to answer bot sometimes. It turns out that that notion of weak versus strong RLDC, those two notions are not actually equivalent for insertion and deletion code. So we prove a separation here. And in particular, the strong lower bounds do have the strong insertion deletion codes. So those that satisfy all three properties must have exponential length, even though we are talking about relaxed versions and constantly many queries. But the weak variants actually behave like the Hamming variants. Okay, so next I want to say, I want to, there was a question. So I want to give you a little bit of intuition about what we can say about queries in this case. So when we looked at all these algebraic families, the queries looked very nice. We were restricting to subspaces, to lines. There was a lot of structure on the queries, and there was a lot of algebraic structure. What happens in the case of insertion deletions? It turns out that all of that is kind of lost. We have no algebraic structure to work with. But there are other interesting things happening here. So let me start by saying that, okay, so we're going to be looking at error patterns, deletion patterns that are going to make the decoder work hard. Okay, so that's how we're going to think about lower bounds. We're going to come up with families with distributions over the error patterns that will make the decoder perform many queries. And I'm only going to talk about this error pattern, which is a very basic pattern. You pick a random number E and chop off that many positions from the received word at the beginning. Okay, so you receive this, and then you just delete E many entries from the beginning, and this is what you receive. Okay, so what can we say about this error pattern? If we look at the queried indices, I'm denoting them here as K and K plus D. K plus D means really distance D from K. So the first query is at position K, and then I'm counting D many positions from K, and that's where the second query is. And for this particular error pattern, if I query the tuple K and K plus D, it should have come from a tuple upstairs, right? So in the uncorrupted code word that is of the form K plus E and K plus E plus D. So the observation here is that the distance between queries stays the same, right? So we have a distribution of queries here that induces another distribution upstairs. Essentially, we need to understand such distribution, distribution. So one may ask, can we come up with insdel LDCs for this particular error pattern? So it's just a simple type of errors that you are allowed to make. It turns out that some massaging of the Hadamard code that we've seen before actually does work. So if you recall to decode at position I, you pick A and A plus E. Plus here means, A plus EI, so plus means binary addition here. Here is kind of the analog of what you need to do to decode from insdel errors. You pick a random pair at distance 2 to the I minus 1. So we assume lexicographic ordering. It turns out that that with some massaging, the Hadamard code is a local decodable code when for this particular error pattern. So what I'm trying to get at here is that algebraic structure kind of gets thrown out of the window, but there is more of some sort of a geometric structure here. So the queries have distance, like other notions of distance between them. Okay, so that's and the final proof that you need to work harder to come up with distributions of errors that provably will require you to make exponentially many queries. Okay, that's the strategy of the proof. So quickly summarizing what we've seen so far, you can transform a Hamming LDC into an insdel LDC with a polylog M blow up, but constant loss in rate and distance. This has no implication in the constant query regime, but we have now results that are exponential lower bounds for constant queries, the LDCs. And in that paper, we actually conjectured that there do not exist constant query LDCs. And this was recently proved in a breakthrough result of Meghal Gupta, who's a student here at Berkeley. She shows single-handedly that constant query insdel LDCs do not exist by kind of taking our techniques to the next level. This is a very impressive work, and it's also just a very recent paper. So there are still questions like what exactly you can still get between constant and polylog, what can you construct, what other lower bounds one can prove. Another thing that we've been interested in and didn't get far is applications. So Hamming LDCs have lots of applications throughout DCS. Can we come up with any analogies that are meaningful in the INSDAL version? Probably in the data structure world, one can, but it would be interesting to see what else can be done with INSDAL LDCs.
A quick question, I probably missed that. What is theta of one loss in decoding radius?
Oh, I mean, just constant blow up in the rate and distance.
In the distance, it will go down.
Yeah, distance will go down.
What was it actually like? What was the original?
The constant. I mean, it's constant.
Goes down from a constant to another constant.
So it's just a transformation. You take your Hamming LDC, and
Just thinking like Hamming LDCs, what is the decoding radius? Isn't that just one?
no, the distance, not the decoding. Oh, I said decoding radius. Sorry, distance. Sorry, yeah, this should be distance.
I see. So the distance would
Oh,
become
sorry.
what to what?
So sorry, it's the amount of error, right? So a loss in the rate and the amount of error that you can withstand. And so if you withstand with a previous LDC, yeah, it's just,
Okay. I got it. Oh,
yeah,
sorry.
that's okay, yeah. More questions? Okay, so, okay, I think this time I went really fast. I'm here talking about codes for distributed storage and erasure coding. And this dramatic picture it is courtesy of Mahdi, who it's apparently ChatGPT generated. When you ask it for distributed storage, it's supposed to show a better for distributed storage. So anyways,
So what are those things?
I don't know.
Wow.
No, these are drones, right? Yeah. Yeah, they're erasing some data centers. It's a very, yeah, exactly. Yeah, it's the worst case. But let me tell you about the worst case. It makes sense. So, okay, so codes for distributed storage. So there are a couple of desideratas that we'd like to have when we talk about distributed storage. And in particular, data centers are hierarchical. We want to kind of model that. Failures are viewed as erasure. We know whether a node failed or not, so it's an erasure. And here, unlike the locally decodable setting, we don't care about asymptotically many errors or here erasures, but we typically care about constantly many, so like 1, 2, 3. Small number of erasures that we want to kind of very quickly fix. And we kind of also need to capture recovery from nearby chunks of data. And we also need to be resilient to many erasures globally. So if something bad happens, like in that picture, globally, we still want to be able to recover. So pictorially, we can think of erasure codes in this manner. We have data broken into chunks of kind of small size, and we add some parities that are parities only on the bits of the chunks. And then we also need to add some global parities. So these are parities over bits that could belong to multiple chunks. So chunks at larger distance. Okay. So an LH local reconstruction code that encodes K symbols into N symbols has to correct H+1 simultaneous errors, and it needs to recover any single erased symbol by accessing at most L other symbols. So kind of this smaller chunks are supposed to be of size little L, and the bigger the global parities are supposed to correct these additional erasure patterns that might not be not necessarily locally. Okay, so as an example, starting from Reed-Solomon code, we can get somewhere close to this goal, but so these are called pyramid codes. What we can do is recover message bits. And the idea is as follows. So we start with a Reed-Solomon code. Okay, so an NKD code. It has K, sorry, I mean to say D-1 parity checks. So N is N minus D+1, it's an MDS code. It has D-1 parity checks. Now assume that one of these parity is a global parity in the sense that it's like the XOR of every single bit. And we're going to replace this global parity by more local parities. So replace it by, let's say, K over L, many local parities, one per chunk. Let's assume that K is divisible by L. And therefore, we get a code of length, just what we had before, K plus D-2, these global parities, plus K over L, these local parities. And it turns out that such a code does match the singleton bound for LRCs, which I'm actually going to talk about next. And it has the property that each message bit can actually be recovered from L other bits. But you cannot recover locally the global parities. Okay, so Reed-Solomon codes get us some leverage, but more work needs to be done. So the singleton bound for LRCs looks as follows. So as before, in the classical setting, the amount of redundancy is at least D-1. Here, the amount of redundancy is at least K over L plus D+2. So if you replace L by K, if you actually don't have any locality, you recover the singleton bound. And in a beautiful work of Tamo and Varg in 14, they came up with an explicit construction of codes that achieve this bound using a subcode of Reed-Solomon code. And what's interesting here, or what people care about here, is also the size of the field. So we want fields that are of small size, and they achieve this with linear size fields. Okay. Now, another question that people ask when they think about LRC codes is, what among all LRC codes that have the same parameters, which ones are better? So there are some that correct some erasure patterns, some that correct other erasure patterns. Is there a code that corrects all possible correctable erasure patterns? And such a code is called the maximally recoverable codes. And it turns out that such things do exist. So maximally recoverable codes exist. But the caveat is that they exist. I mean, the basic proof only shows the existence of such things over large fields, exponentially large fields. Okay, so one of the big questions in this area is what is the smallest field size for maximum recoverable locally maximally recoverable LRCs, and can we come up with explicit construction? So this is actually not an explicit construction. Okay. So there is a lot of work in this area, and I should just point you to experts in the audience, like Arya and Mary has worked in this area, and of course Venkat, who has worked on everything. And so there are many works that are incomparable, but some kind of more uniform constructions, so constructions that work over all ranges of parameters, come from these two papers. And the bound that they get looks like this. I mean, it looks a bit weird, but think of L as being a constant, for instance. Locality, we care about small locality. This would give us N to a minimum number of global parities. L is the length of the local group, and A is a number of parities, so A is always smaller. A is the number of parities inside each local group. So I showed you for Ritz-Solomon just one parity, but you could have many more parities inside each local group. So these LRCs work for correcting up to alpha erasures in each local group and 8 additional global parities. Okay, so of practical interests, again, A being 1 to 3 and H being small, these are very common settings. So for such bounds, we get kind of polynomial size fields. So that's not too bad. There is also work on lower bounds, and there are some lower bounds that are super linear for some ranges of parameters that I'm not going to get into. So in terms of strategies of proving upper and lower bounds, this is something I just pretty much every paper looks at this matrix. If you think a little bit about it, the parity check matrix of such codes has this nice form. So basically, it's very sparse, and the local groups, the parity on local groups is associated with these small matrices AI that kind of come off a diagonal, and then the global parities are captured by kind of the last matrices, B1, B2, BG here. And so BIs and AIs have appropriate dimensions. And the strategy from here on is to analyze determinants of these matrices or rank of these matrices when the AIs and BIs have kind of special forms, nice forms. And in particular, some of the matrices that appear again and again in these papers are matrices that look like Vandermonde, which are nice because their determinant is non-zero if the alpha i's are are not, if the alpha i's are distinct. And there are generalizations over finite fields, let's say if q to the n here. So these are matrices whose determinant is not non-zero when the alpha i's are linearly independent over fq. There are the recent paper that I just mentioned here, the kind of recent breakthrough in this area, uses something called skew polynomials. These are polynomials that have roots of very special structure. They form subspaces, and they they're kind of really hard to to understand. I wanted to put something for you to see, but they're not that easy to describe. So there is a whole theory developed in this paper, or it's been developed before, but they kind of rewrite it in a way that is attractive to DCS. And it's probably the case that such polynomials will have further applications. This is actually my last slide. I think this time I went too fast, while last time I went too slowly. But anyways, we haven't talked about many other local codes that people have considered. So local regeneration codes, these are also codes for erasure for distributed data, but where instead of the number of servers accessed, we care about the communication performed between the servers. So we want to minimize the communication. Locally updatable codes, so these are codes that are more relevant to cryptography. It's about kind of locally changing a code in order to get to another code. Approximate local decoding, local list decoding, that's again something that I haven't covered at all. So this is in the setting when we go beyond unique decoding, the amount of error is larger than half the minimum distance. Local codes in computationally bounded channels. These are codes also kind of more relevant to cryptography in the setting where the adversary doesn't have all the time in the world to come up with the worst case erasure pattern, but it's time bounded. It has to come up with an erasure or the worst erasure or like error pattern within a time bound or within a space bound. And so what can we do in that setting? Finally, there is work on quantum locally decodable codes, and very recently I saw a paper again by Venkat on quantum locally recoverable codes. And yeah, so there is a ton of work out there. The conclusion of the talk is that we've just scratched the surface. So anyways, that's it from me. Thank you for your attention.
Again, we have time for questions. I have a question actually going back quite a bit. You had this thing about the insertion deletions. You asked, can you beat the noisy binary search?
Mm-hmm.
And you didn't say much about it, but I think on your slide it said you can. If I saw that right. And I was wondering if you can say a bit about.
Where did I say that? It's after.
Or maybe I read it wrong.
No, it's before.
So it was in some parameter range.
Right.
It was possible to beat the noisy binary search. I just wanted to add, the question was, what's the trick?
We don't know. I definitely shouldn't have said that you can. It's an open question.
Oh, then I misread it.
Yeah, it's somewhere.
Yeah. Yes.
Somewhere here it should be.
There.
Okay. Yeah, is binary search inherent to instant LDCs?
No, I thought it was after this, was like a lot, we can talk about it later.
I think I talked about relaxed locally decodable codes. Relaxed locally decodable codes. Okay.
So it was relaxed, okay.
Yeah, for the relaxed version, you can get constant queries. So if you just need to satisfy the first two property of relaxed decoding, which is completeness and the fact that for each message bit, you should output either the correct bit or bot with probability 2/3. So that's the weak version. You can actually you can build it in the sense of that there are constant queries, such things.
And then what's the trick there? I mean, 'cause it seems.
So the trick there is that you can say a lot of bot. You can respond with bots as soon as you detect an error. So the third property said that each message bit, the number of message bits that should actually be decoded correctly with probability at least half plus epsilon should be a constant fraction of all the message bits.
Yeah.
But if you drop that, kind of all bets are off. If you don't care what you're going to see, I mean, you can have bots all the time, and that satisfies the, yeah, exactly. Yeah.
Can you say a little bit about what locally updatable means? Because it sounds like
It's kind of so it's a tension, right? So I actually don't know the crypto setup, but yeah, there is a tension because they should be far from each other, yet you want to get to a code word. So I don't know exactly the setup. I just kind of did a search on local codes and ran into locally updatable codes. But yeah, I don't actually know what to call it. More questions?
All right, if not, we'll take anything else offline and thank Elena again.